Everything around us consists of matter. From living organisms to the air we breathe, all this matter is made up of atoms. When these atoms bind to each other, they form molecules. Knowledge of the behavior of molecules is key to understanding the world around us. By using a technique called nuclear magnetic resonance, or NMR for short, we're able to see these molecules, zoom in on their smallest details, and observe how they behave and interact in all kinds of matter. NMR has a wide variety of applications. It's very valuable in cancer research, where it is used in the development of smart delivery systems for drugs. NMR can even help us to understand the molecular basis of photosynthesis in plants and algae, thus making it possible for us to know which crop strains are best suited for different environments. Another completely different usage is during the invention of a new generation of batteries. Here, NMR plays a crucial role in establishing the molecular details of the battery's energy-storing function. But how does nuclear magnetic resonance actually work?
Molecules are built up of atoms. When molecules are placed in a strong magnetic field, the nucleus of some atoms will start to behave like a small magnet. If next, a broad spectrum of radio frequency waves is applied, the nucleus will start to resonate at its own specific frequency. You can compare this to the use of a tuning fork, where a guitar string will resonate only in response to a tone of exactly the right frequency. We measure the resonant frequencies of nuclei and convert them into an NMR spectrum that displays all the relevant frequencies as peaks. The height of each peak represents the amount of nuclei that resonates at a certain frequency, what we call the intensity of the signal. The more resonating nuclei, the higher the intensity, similar to the louder sound of 10 guitars as opposed to 1. The value of the frequency at which a nucleus resonates, in other words, the tone, gives us information about the surroundings of the atom in question, such as its neighboring atoms and their relative position. When atoms are really close together, their nuclei can even cause each other to resonate. By measuring these so-called cross peaks, we can determine the three-dimensional structure of molecules and observe how molecules move.
By using ever stronger magnets, we can study more complex molecules in more and more detail. Ultimately, this will provide us with answers to some of today's vital questions. How can we ensure that drugs are only active in the specific areas of the body? How can we make batteries more energy efficient and reduce the need for fossil fuels? How can we better prepare for the consequences of climate change? To achieve all this, 5 Dutch universities have joined forces with the private-public partnership COAST to install a brand new 22 Tesla magnet at Utrecht University. This mega magnet represents a huge step forward in the attempt to find detailed answers to open questions that are all important for our future.